Imagine standing on the surface of the moon. No wind, no sound, no birdsong, no rustle of leaves, no distant hum of traffic. Nothing. Just a silence so complete it presses against your eardrums like a physical weight. A silence so total that the only thing you can hear is the sound of your own breathing amplified inside your helmet. The sky above you is not the pale blue you've known your entire life. It is black, not the soft, star-scattered black of a clear night back on Earth. This is something else entirely. This is absolute black, the black of infinite vacuum, a darkness so deep and so final that it makes your depth perception dissolve. You cannot tell where the sky ends and something else begins, because there is no boundary. There never was. The horizon curves away from you in every direction, sharper and closer than you expect, because the moon is small and the mathematics of its curvature are merciless. You are standing on a world that is barely a quarter the diameter of Earth, and that smallness is immediately, viscerally apparent. The ground beneath your boots is a fine gray powder, not sand, not gravel, not anything that has an easy earthly name. It is something older than almost everything you can conceive of. This material, scientists call it regolith, has been lying here, undisturbed in the deep sense of the word, for geological ages that make human civilization look like a rounding error. The top layer, the stuff your boots are sinking into right now, was last significantly disturbed hundreds of millions of years ago, when a micrometeorite the size of a grain of sand struck nearby and threw a gentle spray of powder across the surface. Since then, nothing. No water, no wind, no erosion, no life. Just the slow, imperceptible work of cosmic rays burrowing into the top few meters of soil, and the occasional tick of a distant impact somewhere over the horizon. It looks peaceful. It looks still. It looks, from a distance of 250,000 miles, like a gentle, welcoming companion hanging in the night sky. And that stillness, that apparent calm, is the most dangerous lie in the entire solar system. We grew up thinking of the moon as friendly. It's right there, hanging in our sky every single night, close enough that we can see its ancient craters with a cheap pair of binoculars bought at a gas station. We've been there. We planted flags in that powder, flags that still stand today, though the ultraviolet radiation has long since bleached them white. We drove an electric car across its surface. We hit golf balls into its dust. Alan Shepard, standing on the Fra Mauro Highlands in February of 1971, swinging a 6-iron with a gloved hand, the ball sailing away into the black sky in the weak gravity. 6-iron shot traveling further than any golf shot in human history, and nobody will ever see it land because it's still out there. 12 people walked on the moon. They brought back 382 kilograms of rocks and dust and core samples. They came home. They held press conferences and went on world tours, and eventually, some of them became professors and some of them became businessmen, and all of them lived long lives. So, yes, it feels conquered. It feels safe. It feels like a solved problem, a chapter we already wrote, something that belongs to the past tense. It is neither of those things, because the 12 astronauts who walked on the moon didn't stay long enough to learn what it actually does to you. The longest single stay on the lunar surface, Harrison Schmitt and Eugene Cernan of Apollo 17, the last humans to walk on the moon, was 75 hours, 3 days, a long weekend. They were gone before the moon had time to properly introduce itself. And what we've discovered in the decades since, from laboratory analysis, from robotic missions, from the long-term health data of the Apollo astronauts themselves, should make every one of us think very carefully before we ever send anyone back to stay. The dust. The problem started before the astronauts even got back inside the spacecraft. Every single Apollo crew reported the same thing, with a consistency that should have alarmed mission planners far more than it apparently did. The dust. It got everywhere. It coated their suits in a fine gray film that no brush could adequately remove. It crept into the seams of their equipment, clogging joints and mechanisms that had been precision engineered to work in the vacuum of space. It scratched their helmet visors, those critical windows onto their environment, leaving fine abrasion marks across the polycarbonate. It jammed their sample containers, making it difficult to seal rocks that had been collected at considerable effort. When the astronauts tried to brush the dust off their suits before re-entering the lunar module, a reasonable precaution, it clung harder. Electrostatically attracted to everything it touched, it resisted every attempt at removal. It was as if the moon did not want to let go. When the astronauts brought their suits inside the lunar module and finally unsealed their helmets, breathing the cabin air for the first time in hours, the dust that had accumulated on their suits became airborne in the low gravity and stayed airborne. It drifted through the cabin like smoke that refused to settle, like a fine gray fog that had no intention of landing anywhere. In Earth, gravity, dust settles. On the moon, in 1/6 gravity, the finest particles hang suspended in the air indefinitely, catching the light, infiltrating every breath. Harrison Schmitt, the geologist astronaut on Apollo 17 and the only professional scientist to walk on the moon, developed what he described as lunar hay fever within hours of exposure. His eyes burned with a persistent irritation that eye drops couldn't fully relieve. His sinuses swelled shut, making every breath a labored exercise. He was sneezing uncontrollably, his sneezes muffled and strange inside the cramped lunar module. Other crew members across multiple missions reported sore throats that appeared suddenly and without prior illness, watery eyes that made it difficult to read instruments, and congestion that persisted not for hours, but for days after returning to Earth. Jim Lovell, who didn't walk on the moon but reviewed the mission reports carefully, later noted that the dust problem was one of the most consistently reported and least adequately solved challenges of the entire Apollo program. And every single one of those astronauts described the same strange, distinctive smell when they first opened their helmets: burnt gunpowder. The sharp, acrid, sulfurous smell of a freshly fired weapon. Not pleasant, not subtle, immediately noticeable and instantly memorable. That smell was chemistry in action. On the lunar surface, where there is no atmosphere and no moisture and no oxygen, the soil exists in a state of chemical suspended animation. It has been in this state for billions of years. Billions of years of micrometeorite bombardment, not single large impacts, but an unending rain of particles ranging from microscopic to sand grain-sized, striking the surface at velocities that exceed anything achievable in terrestrial laboratories, have ground the lunar rock into particles of extraordinary fineness. We're talking about grains that average 5 to 10 micrometers in diameter. For comparison, human hair is roughly 70 micrometers wide. A single grain of this lunar powder is about 1/7 the width of a human hair. The finest particles are smaller than 1 micrometer, smaller than most bacteria. But it's not just the size, it's the shape. On Earth, particles get tumbled in rivers, smoothed by wind, rounded by contact with water and other particles. They become smooth, benign. The moon has none of these processes. No water, no wind, no softening mechanism of any kind. Each grain of lunar regolith is a tiny, jagged shard of broken volcanic glass, with edges and points so sharp and so intricate that an electron microscope is required to fully appreciate them. When those particles finally encounter moisture, the moisture inside an astronaut's sinuses, the fluid lining of a lung, they react. The fresh, chemically reactive surfaces that have been waiting in suspended animation for billions of years suddenly find themselves in contact with something wet, something biological, and they respond with chemical aggression. They bond to surfaces. They bond to tissue. And unlike ordinary dust, which your body has evolved to deal with, the cilia in your airways, the mucus layers, the immune responses, the moon's particles are so fine, some smaller than a single micron, that they bypass every defense mechanism your body has. They can penetrate past the bronchial tubes and into the deepest recesses of the lung, into the alveoli where gas exchange happens, into tissue where your body's defenses can't reach them, and your body's cleaning mechanisms can't expel them. In Earth's gravity, inhaled particles eventually settle out of the air and get cleared through normal respiratory function. In the moon's weak gravity, 1/6 of Earth's, those same particles hang suspended in the air far longer than they would at home, greatly extending the window of potential inhalation. And once they're in the lower respiratory tract, gravity is no longer helping you clear them. NASA took this seriously enough to establish a dedicated research group, the Lunar Atmosphere and Dust Environment Explorer Program, and later the Lunar Dust Toxicity Advisory Group, specifically to study the biological implications of lunar dust exposure. What they found was complicated, and some of what they found was genuinely alarming. The dust contains silicate compounds similar to crystalline silica, the substance responsible for silicosis, a progressive, irreversible, incurable lung disease that has killed miners and quarry workers for centuries. It also contains nanoscale iron particles embedded in the glassy shells of the soil grains, which are highly chemically reactive. Research on lunar simulants, Earth materials engineered to approximate the properties of actual lunar regolith, suggests the dust acts as a physical irritant at minimum. At higher or prolonged exposures, the potential for chronic respiratory damage is not theoretical. It is a serious concern that remains, as of 2026, an open and unresolved question in space medicine. One recent study from the University of Technology, Sydney, found that lunar dust simulants were cytotoxic, cell-killing, to a degree somewhat less severe than urban air pollution in Sydney on a bad day. Which sounds reassuring until you remember that the Apollo astronauts had no air filtration systems, no sealed airlocks, and no effective way to keep the dust out of their lungs. Future missions will be longer. Artemis surface stays are planned for weeks rather than days. Future exposure will be substantially greater. And the dust from the permanently shadowed craters near the lunar South Pole, regions where no direct sunlight has penetrated for billions of years, where temperatures hover near absolute zero, where the chemistry and physical properties of the regolith may be dramatically different from what Apollo encountered, has never been directly sampled. Nobody knows what it contains. Nobody knows how it behaves. Nobody has tested it. We are planning to send people to stand in these craters while our understanding of their dust remains essentially at the level of educated speculation. The living dust. The dust also does something that borders on science fiction. On the sunlit side of the moon, solar ultraviolet radiation, intense, unfiltered, relentless, strikes the surface with enough energy to knock electrons directly off the surface of the soil particles. This process, called photoionization, gives the ground a positive electrical charge. And the finest dust grains, the particles measuring less than a micron across, the ones most dangerous if inhaled, pick up enough electrostatic charge to be literally repelled from the surface. They are launched upward by their own electrical charge into the vacuum above. They hover, they float, they persist. Some theoretical models suggest these electrostatically levitated particles can reach altitudes of hundreds of meters, possibly even kilometers, forming a thin but persistent envelope of charged floating glass around the entire moon. Observations from the Lunar Atmosphere and Dust Environment Explorer mission, which orbited the Moon specifically to study these phenomena, found evidence of unexpectedly dense dust populations at unexpectedly high altitudes. The Moon carries its dust with it, like a persistent haze no eye can detect. On the dark side of the Terminator, the process reverses. Electrons from the solar wind accumulate on the surface, giving it a negative charge that can launch particles by electrostatic repulsion in the opposite direction, sending them even higher. At the Terminator itself, the precise boundary between lunar day and lunar night, the line where shadow meets sunlight, horizontal electric fields generated by the sharp difference in surface potential may drive dust particles sideways across the surface in patterns that researchers have described, with appropriate caution, as a kind of lunar dust storm. Not a storm in any atmospheric sense. There is no atmosphere to drive it. A storm of pure electrical energy, lifting and driving particles without a single molecule of air involved. The Moon isn't just covered in dangerous powder. The powder is alive with electrical energy, constantly lifting, constantly drifting, constantly resettling and relaunching. You cannot simply wait it out. You cannot simply cover up. The dust is not passive. It actively seeks your suit, your habitat, your equipment, driven by forces you cannot see and cannot fight. Radiation, the invisible killer. Now add radiation. The Moon has no magnetic field to speak of. Its core is largely solid and cold, having radiated away most of its primordial heat over billions of years. Without a spinning, conducting liquid core, there is no dynamo, and without a dynamo, there is no magnetic field. And without a magnetic field, without the invisible electromagnetic bubble that surrounds the Earth and deflects the constant particle bombardment from the Sun and the galaxy, everything gets through. On Earth, we are protected by two shields working in concert. The first is the magnetic field, the magnetosphere, which deflects charged particles around the planet entirely, sending them harmlessly spiraling along field lines to the poles. The second is the atmosphere, 78% nitrogen, 21% oxygen, and the rest a mix of noble gases and trace elements, all of it adding up to a layer of air roughly equivalent in shielding effectiveness to 3 meters of concrete. Between these two shields, we are so thoroughly protected from cosmic radiation that most people go their entire lives without ever thinking about it. On the Moon, you get the full dose, unfiltered, undiverted, all of it. Galactic cosmic rays are the most exotic component of this radiation environment. They are the nuclei of atoms, protons, helium nuclei, and heavier elements like iron and silicon that have been stripped of their electrons and accelerated to velocities approaching the speed of light by the shock waves of ancient supernova explosions in distant parts of the galaxy. They arrive from all directions, continuously, carrying energies so high that they pass through spacecraft walls and through human tissue as if the material barely existed. They shred DNA strands as they go. A single high-energy iron nucleus tearing through a cell can leave a track of ionized, damaged molecules stretching across multiple chromosomes simultaneously. Damage far more complex and far harder for the cell to repair than the single-strand breaks caused by lower-energy radiation. And here is the cruel irony that makes engineers want to despair. Unlike solar ultraviolet radiation, which you can block with a visor, or even lower energy particles, which additional shielding can reduce, cosmic rays do not simply stop when they hit a wall. When a high-energy cosmic ray strikes a thick metal wall, it doesn't stop. It shatters atoms in the wall. It initiates a cascade reaction that produces what physicists call secondary radiation, showers of neutrons, gamma rays, pions, and charged fragment particles that scatter in every direction, including inward. Thicker armor generates more of these secondary particles, not fewer. At a certain shield thickness, you end up delivering more total radiation dose to the person inside than you would if there were no shielding at all. This is not a theoretical problem. This is a real, measured, experimentally confirmed phenomenon that has been studied extensively for both space applications and for particle accelerator facilities. It means that the intuitive solution, build thicker walls, is not a solution. The engineers building the habitat for future lunar residents cannot simply add more steel and call it solved. Shielding against galactic cosmic rays is widely acknowledged to be one of the hardest unsolved engineering problems in human deep space exploration. The most promising current approaches involve using water, or polyethylene, hydrogen-rich materials that absorb the secondary particles better, or burying habitats under meters of regolith. Both approaches come with significant practical complications. On top of this constant, unavoidable background radiation, there are solar particle events. These are eruptions from the sun, coronal mass ejections and solar flares, that can, in a matter of hours, flood the interplanetary space environment with high-energy protons at fluences that would deliver radiation doses orders of magnitude above the background. They are essentially unpredictable on timescales of days. Forecasters can sometimes see the precursor signs of a major eruption, but the warning time is measured in hours at best, and a major event can develop faster than any reasonable response plan. On the International Space Station, astronauts retain some residual protection from Earth's magnetic field. The ISS orbits at an altitude where the magnetosphere still provides meaningful shielding at certain latitudes. On the Moon, no such protection exists. A major solar particle event could deliver a potentially lethal radiation dose to an unshielded astronaut in less than a day, not over years, in hours. The Apollo missions were extraordinarily lucky. They flew during periods of relatively subdued solar activity. The August 1972 solar storm, one of the most intense proton events of the 20th century, the kind of event that occurs perhaps once per solar cycle, occurred in the gap between Apollo 16, which had landed in April, and Apollo 17, which would launch in December. Had any Apollo crew been on the surface during that August storm, the radiation dose they would have received in their relatively thin-walled lunar module and spacesuits could have been fatal. The storm missed the astronauts by months, not by design, by luck. As we plan longer missions, weeks on the surface, eventually permanent occupancy, the probability that we will again be lucky enough to miss every major solar event approaches zero. The strategy of hoping for calm solar weather is not a strategy. It is wishful thinking dressed in engineering language. Temperature, a world with no mercy. Then there is the temperature. On Earth, we live in a world so thoroughly buffered by its atmosphere that we rarely stop to appreciate what the atmosphere does for us. Air traps heat. Air distributes heat. Air moderates the extreme swings that would otherwise follow from the planet rotating through sunlight and away from it. Even in the most extreme climates on Earth, the Sahara at noon, Antarctica at winter solstice, the atmosphere is doing constant, invisible work to keep the temperatures in a range that does not immediately destroy most matter. The Moon has no atmosphere, none whatsoever. The pressure on the lunar surface is approximately 3 times 10 to the minus 15 times the pressure at sea level on Earth. It is, for practical purposes, a vacuum. And in a vacuum, the only way heat can transfer is by radiation. There is no air to conduct warmth from the sunny side to the dark side. There is no air to smooth out the transitions. During the lunar day, which lasts approximately 14 Earth days, because the Moon rotates so slowly, the surface exposed to direct sunlight bakes to roughly 127 degrees Celsius. That's 260 degrees Fahrenheit. Well above the boiling point of water, hot enough to cook food, hot enough to destroy many plastics and to accelerate the degradation of rubber seals and metal joints. During the lunar night, another 14 Earth days of darkness, temperatures plunge to approximately negative 173 degrees Celsius. That's negative 279 Fahrenheit. Cold enough to liquefy oxygen if the pressure were right. Cold enough to make steel brittle and to cause most lubricants to solidify completely. That's a swing of 300 degrees Celsius every 2 weeks, endlessly, without variation. For comparison, the most extreme temperature swings ever recorded on Earth, in places like Verkhoyansk in Siberia, span roughly 100 degrees over an entire year. The moon exceeds 3 times that every 14 days. Every material exposed to the lunar surface undergoes this thermal cycling continuously, and thermal cycling is one of the most reliable ways to destroy things. Metals expand and contract with changing temperature. If they expand and contract by different amounts, if a bolt expands more than the plate it's bolted to, for instance, the joint loosens, the seal fails, the structure weakens. Over thousands of cycles, even materials specifically engineered to handle thermal stress develop fatigue cracks and ultimately fail. The Apollo missions lasted days. The longest surface stay was Apollo 17 at 75 hours, less than a week. The equipment survived, but it was used for 75 hours, not for years. NASA's Artemis program plans surface stays of weeks. A permanent base would need to survive for decades. And across decades, those 14-day temperature cycles accumulate. Every joint, every wire, every seal, every circuit board would be tested continuously by thermal stresses that no Earth-based engineering test can fully replicate, because you cannot put an entire base in a vacuum chamber and run it for 30 years. The Apollo astronauts found that the dust had physically abraded through layers of their spacesuit boots, the outermost protective layers, in just a few days. The vacuum seals on their sample containers were damaged by abrasion from dust particles beyond their intended use life. This was on missions lasting 3 days. Extrapolate that abrasion rate to a year, to a decade. The numbers are not encouraging. A shrinking, shaking world. And the moon itself, the stable, dead, geologically inert rock we grew up assuming it was, is not stable. It is not dead. It is not inert. It's shrinking. As the moon's interior cools, slowly releasing the heat it has held since its violent formation 4.5 billion years ago, the entire body contracts. Over the last few 100 million years, this cooling has caused the moon to lose more than 45 meters of circumference. 45 meters. That sounds like a trivial change for a world with a circumference of more than 10,000 kilometers, and in one sense, it is. It's a change of less than 0.5%. But the consequences of even that small change are severe because of something fundamental about the moon's geology. Unlike the Earth, the moon does not have tectonic plates. Earth's crust is broken into large moving sections, the tectonic plates, that can slide past each other, subduct beneath each other, and generally absorb the stresses generated by the planet's internal changes. This plate system acts as a kind of global shock absorber, distributing and releasing stress across thousands of kilometers of active fault zones. It's why Earth has earthquakes and volcanoes. They're the expression of all that stress finding release. The moon has none of this. The moon's crust is a single, continuous, brittle shell. And when the interior shrinks and the crust needs to accommodate the reduced volume, it cannot flex because it is too rigid and too cold to flex. Instead, it cracks. Sections of crust are shoved up and over adjacent sections, creating steep, irregular cliff faces called Lobat scarps. Compressional thrust fault features that can stretch for hundreds of kilometers across the surface. The Lunar Reconnaissance Orbiter, which has been mapping the moon in extraordinary detail since 2009, has identified thousands of these lobate scarps. Thousands. They are found at all latitudes, in all orientations, distributed across the entire surface. And many of them are geologically young, fresh enough in geological terms that the craters on top of them are small and few, indicating they formed relatively recently. This is not a finished process. The moon is still contracting, the stresses are still building, the cracking is still happening, and cracking produces moonquakes. Not the deep, faint tremors that Apollo's seismometers detected in the 1970s. Those deep moonquakes, originating hundreds of kilometers below the surface, are well understood and relatively benign for surface operations. What matters for future human habitation is a different category entirely: shallow moonquakes, originating just a few kilometers below the surface along active fault lines. These are the dangerous ones. In 2024, a landmark study led by Thomas Waters at the Smithsonian National Air and Space Museum and Nathan Williams at NASA's Jet Propulsion Laboratory systematically analyzed the Apollo seismic data with modern algorithms and linked one of the strongest shallow moonquakes ever recorded, a magnitude 5 event recorded in 1977, to a cluster of young thrust fault scarps in the lunar South Polar region, the same region that NASA has chosen for the Artemis 3 crewed landing. Specifically, the data suggests the epicenter of that 1977 quake may have been within a few kilometers of candidate Artemis landing site peaks near the Shackleton crater complex. One of the formally listed candidate landing sites, Daggerlasha Rim 2, sits in uncomfortably close proximity to an identified young fault scarp, and a moonquake is not like an earthquake. On Earth, seismic energy travels through a crust that contains water in its rock matrix that has been kneaded and processed by billions of years of geological activity, that has a plastic, somewhat yielding quality that helps absorb and dissipate seismic waves. Earth earthquakes are violent and destructive, but they are generally short. A major earthquake lasts seconds to perhaps a minute or two of intense shaking. Then it stops. The moon's crust is bone dry. It has never had significant liquid water. It has not been processed by plate tectonics. It is fractured and fragmented by billions of years of impact bombardment, but those fragments are loose and unconsolidated. Rubble, really, stacked on rubble. When a seismic wave travels through this loose, dry, fragmented medium, it does not dissipate quickly. It bounces. It reflects. It rings. The Apollo seismometers recorded moonquakes that continued for hours after the initial event. Hours. Not the sharp, violent shock of a terrestrial earthquake, followed by gradual quiet, but a sustained, gentle to moderate vibration that persisted for an entire afternoon. The analogy seismologists use is accurate. It's like striking a bell. Strike a steel bell and it rings. The sound diminishes gradually, but continues far longer than you might expect. The moon rings like a bell when struck, and in a world where the soil is loose, unconsolidated rubble, the gardened, fragmented, churned product of billions of years of micrometeorite bombardment, sustained vibration has a specific, well-understood consequence: liquefaction. Or in the dry, airless case, the equally dangerous phenomenon of loose material losing its structural coherence and flowing. The steep walls of craters become unstable. The talus slopes that ring the insides of impact basins begin to slip. In 2025, the same research team published a follow-up study analyzing the Apollo 17 landing site in the Taurus-Littrow Valley with updated methodology. Their conclusion was striking. The boulder falls and landslides visible in that valley, long assumed to have been triggered by ancient meteorite impacts, were actually caused by moonquakes from the Lee-Lincoln fault system running through the region. Not by impacts. By seismic activity, by the moon shaking itself apart from within. The fault responsible has been producing magnitude 3 events repeatedly over the past 90 million years, according to the geological record preserved in the scarps and the displaced boulders. It may still be active. The researchers estimated roughly a 1 in 20 million chance of a damaging moonquake occurring on any given day near an active fault. That sounds like extremely long odds, but stretch that across a decade of continuous habitation, and the probability of experiencing at least one potentially damaging event rises to roughly 1 in 5,500. That's better odds than being dealt a 4 of a kind in poker. You'd be nervous at a poker table where 4 of a kinds came up that often. You should be at least equally nervous about your lunar base. As of early 2026, Smithsonian researchers have cataloged over 2,600 individual thrust fault ridges across the moon's surface, all formed by the same compressional forces, all evidence of a body still in the process of geological change. The shrinking is global. The faulting is everywhere. The moon is not the quiet, still world it appears to be. It is a world in very slow, very relentless geological distress. The micrometeorite rain. Through all of this, the dust and the electricity, the radiation and the temperature swings, the seismic risk and the faulting, there is also the micrometeorite rain. On Earth, our atmosphere is a remarkably effective shield against small space debris. A particle the size of a grain of sand entering Earth's atmosphere at orbital velocity encounters air resistance that generates enormous frictional heat, and the particle burns up long before it reaches the ground. This happens constantly. Roughly 100 tons of material falls from space into Earth's atmosphere every day, and almost none of it makes it to the surface. We occasionally see the streaks of light this produces and call them shooting stars, and they are beautiful, and they are absolutely nothing to worry about. On the moon, there is no atmosphere. There is nothing to stop anything. Micrometeorites, particles ranging from microscopic to sand grain sized, strike the lunar surface at velocities of up to 10 kilometers per second. That is 36,000 kilometers per hour. That is roughly 10 times faster than a rifle bullet. A grain of sand traveling at 10 kilometers per second carries enough kinetic energy to vaporize itself completely and excavate a tiny crater many times its own size in the surrounding rock. These impacts have been happening continuously for over 4 billion years. This is, in fact, what created the fine-grained regolith we've been discussing. 4 billion years of these tiny impacts, grinding the surface rock into powder. For a habitat or a spacesuit, the risk from any single particle is small on any given day. But over months and years, the cumulative effect is not small. It is significant and measurable. The Apollo astronauts found, in the course of their 3-day surface stays, that micrometeorite abrasion had worn through layers of their spacesuit boots. The outermost protective layers, which were designed for this environment, had been abraded by the constant sandblasting of electrostatically levitated dust grains and micro-impacts to a degree that alarmed mission engineers reviewing the post-flight data. The vacuum seals on their sample containers, engineered to close reliably in the lunar environment, were damaged beyond their expected service lives by dust abrasion. A permanent structure on the surface would face this bombardment continuously. There is no maintenance crew that can be quickly dispatched. There is no hardware store nearby. There is no margin for error in a structure whose failure could expose its human occupants to the full lethal suite of the lunar environment. Every surface, every seal, every transparent viewport would be under constant, low-level attack from particles traveling faster than bullets. The only effective countermeasure that doesn't involve completely encasing a habitat in meters of regolith, itself a massive engineering challenge, is regular, difficult, dangerous maintenance by suited crew members working in the very environment that is destroying their suits. This is what the moon actually is. This is what the moon actually is, not the gentle silver companion that poets have written about for millennia. Not the symbol of romantic possibility that lovers have looked up at from every culture in human history. Not the conquered stepping stone that we visited briefly a half-century ago and confidently assumed we understood. It is a world wrapped in glass powder. Powder so fine it passes through your respiratory defenses and lodges permanently in your lung tissue. Powder so chemically reactive it burns the inside of your sinuses on first contact. Powder so electrostatically charged that it clings to every surface and floats on its own electrical energy, constantly hovering, constantly drifting, constantly infiltrating. There is no effective way to keep it out with current technology. Every mission plan that involves human presence on the lunar surface has this as an unresolved engineering challenge. It is a world where radiation pours through your bones every second you stand on the surface. Not the radiation of a dental X-ray or a transatlantic flight. Continuous, penetrating, high-energy particle radiation from a billion-year-old supernova thousands of light-years away. Radiation so energetic that building thicker walls makes the problem worse instead of better. And superimposed on that constant background, unpredictable eruptions from the sun that can, in the span of a single working day, deliver a dose that will kill you over the following weeks. The Apollo missions were lucky. Luck is not a sustainable engineering strategy. It is a world that is quietly tearing itself apart from the inside. 2,600 fault ridges, magnitude 5 moonquakes with epicenters near proposed landing sites, seismic vibrations that ring for hours rather than fading in seconds. Loose, unconsolidated soil on steep crater slopes, waiting for the next seismic event to send it flowing. The same South Polar region we've chosen for human habitation, because it has water ice and relatively constant sunlight, is also the region with the highest density of young, potentially active thrust faults. The water and the danger are in the same place, and we cannot have one without the other. It is a world where the temperature swings from boiling to freezing every 2 weeks without pause and without mercy, where every material, every seal, every joint in every structure must survive thousands of these cycles over the course of a decade-long habitation, where the same dust that infiltrates your lungs is simultaneously sandblasting every external surface at high velocity. We went there 6 times. The longest we stayed was 3 days. 6 brief visits by 12 extraordinary human beings, none of them long enough for any of these dangers to fully reveal themselves. The Apollo astronauts were visitors passing through too quickly for the moon to show them what it could really do. Going back is one thing. Staying is something else entirely. The human body against an alien world. Consider what extended lunar habitation would actually mean for the human body, not in the abstract, but in the specific, physical, day-by-day reality of what biology does when it's placed in an environment it never evolved to handle. Start with gravity. Lunar gravity is approximately 38% of Earth's. That sounds like it should be manageable. You'd weigh about 85 pounds if you normally weigh 220. You could jump remarkably high. Loading a supply crate would feel effortless. But bone and muscle and cardiovascular function evolved over hundreds of millions of years in one gravity. Specifically, in one Earth gravity. Every system in your body is calibrated to that number. 6 months on the International Space Station in microgravity, not lunar gravity, true zero GE, costs astronauts an average of 1 to 2% of their bone mineral density per month. Their muscles atrophy. Their cardiovascular systems weaken because the heart doesn't have to work as hard to pump blood upward against gravity. Their spines lengthen slightly as the vertebral discs decompress. Their vision changes because the shift in fluid distribution caused by weightlessness pushes cerebrospinal fluid toward the optic nerve, causing it to swell and distorting the shape of the eyeball. 38% gravity is better than 0, but it is not enough. Bone density studies suggest that partial gravity environments still result in bone loss, just at a somewhat slower rate. Muscles still atrophy in reduced gravity because the loads they experience are reduced. The cardiovascular changes, the spinal changes, the fluid redistribution effects. These happen in reduced gravity, to degrees we have not yet studied, because no human has ever spent significant time in 38% gravity. The short Apollo stays tell us nothing about these long-term effects. We don't know what 6 months in lunar gravity does to human bone density. We don't know what a year does. We don't know whether the effects are reversible. What we do know, from extensive ISS research, is that microgravity effects require months of rehabilitation to reverse after astronauts return to Earth. Returning from a 6-month ISS mission, astronauts often cannot walk unaided immediately upon landing. They have to be carried from their capsules. They undergo months of physical therapy. That's after 6 months of excellent countermeasures. Daily exercise regimens of up to 2 hours specifically designed to minimize bone and muscle loss. We don't yet have equivalent countermeasures for partial gravity. We don't know what they would look like. We don't know if they'd work. The immune system adds another layer of concern. ISS research has consistently shown that prolonged spaceflight suppresses certain aspects of immune function and simultaneously causes dormant viruses, herpes simplex, Epstein-Barr, varicella zoster, to reactivate in astronaut saliva and blood samples. Stress, both physical and psychological, drives these reactivations. The cumulative stress of lunar habitation, the radiation, the confined spaces, the dust management, the constant vigilance required by a hostile environment, would be substantial. The nearest hospital, in any emergency, is a minimum of 3 days away. In the initial phases of Artemis, realistically longer. The psychological dimension. And then there is the part that is hardest to quantify and easiest to underestimate, the psychological weight of living on the moon. Human beings are extraordinarily adaptable. We have demonstrated this by thriving in environments from the Arctic to the tropics, from sea level to high altitude, from nomadic hunter-gatherer bands to 8 million-person megacities. We are flexible in ways that most species simply are not. But there are limits, and those limits are defined by deep evolutionary programming that doesn't respond to intellectual arguments. The moon is an environment with no natural sounds other than the sound of equipment operating. No wind, no animals, no birdsong or rainfall, or the sound of other human voices except through electronic mediation. The sky is always black, day and night. There is no natural color anywhere. The regolith is gray. The shadows are black. The sky is black. You cannot go outside without a spacesuit, which means you cannot feel wind on your skin or smell air that hasn't been processed by machines. The environment actively reminds you, at every moment, that you are a foreign organism being kept alive by technology in a place that is profoundly indifferent to your survival. Antarctic overwinter cruise, the closest terrestrial analog to long-duration lunar habitation in terms of isolation, confinement, and environmental hostility, experience well-documented psychological effects, anxiety, depression, interpersonal conflict that seems disproportionate to its triggers, cognitive dulling, sleep disturbances, what researchers call winter over syndrome, a kind of low-grade psychological deterioration that settles in after the initial excitement of novelty wears off. These effects occur in people who can step outside, breathe real air, see real sky, and know that weather permitting they could be evacuated. Lunar habitat residents would have none of those safety valves. Add to this the communication delay. The moon is roughly 384,000 kilometers from Earth, and radio waves travel at the speed of light. The round-trip communication delay is between 2.4 and 2.7 seconds. Short enough to be manageable for most purposes, but long enough to make any real-time conversation feel slightly wrong, like a bad phone connection. On Mars, the situation is dramatically worse. One-way communication delay of 3 to 24 minutes, depending on orbital positions. But even the lunar delay is enough to sever the easy, spontaneous connection with Earth that is one of the psychological anchors for ISS crews. Seeing Earth in the sky, the small blue jewel that is everything you have ever known and everyone you have ever loved, hanging above a gray, lifeless horizon, is not purely comforting. it is also a powerful visual reminder of how far away those people are and how thoroughly they cannot reach you. We know from ISS psychology research that the experience of isolation and confinement changes people in ways they often don't fully notice in real time. Mood deteriorates gradually, motivation drops, decision-making quality declines in ways that are subtle but measurable. The first people to live on the moon for months at a stretch will be dealing with all of these pressures simultaneously, while also managing the most technically demanding and danger-laden environment ever inhabited by human beings. But what about robots? At this point, there's an obvious counter-argument. We are aware of it. It is frequently made by people who are uncomfortable with how grim this analysis is becoming. Why send humans at all? We have robots. We have increasingly sophisticated robots. The Opportunity rover survived on Mars for nearly 15 years, far outlasting its 90-day mission design. Curiosity has been operating for over 12 years as of 2026 and is still transmitting data. Perseverance, with its Ingenuity helicopter, is demonstrating levels of surface mobility and autonomy that would have seemed like science fiction a decade ago. China's U-22 rover has been operating on the lunar far side since 2019. India's Chandrayaan-3 mission successfully landed a rover near the lunar South Pole in 2023, the first mission to achieve a South Polar landing. Why not just send robots and skip the part where human beings get killed? This is a reasonable position. For certain kinds of science, systematic survey, sample collection, long-term environmental monitoring, robots are excellent and improving rapidly. A robot can be left on the surface for years without any of the life support, dust management, psychological, or medical concerns that make human habitation so challenging. A robot that fails is a setback. A human that fails is a tragedy. But robots have fundamental limitations. A geologist, a trained human scientist standing at a rock outcrop, hammer in hand, able to look at color and texture and structure, and smell and feel, and make rapid, intuitive judgments based on decades of experience, can accomplish in an afternoon what a rover might take weeks to complete. Human presence allows for improvisation, for real-time problem-solving, for the kind of contextual judgment that no current AI system can replicate in an unstructured environment. The science case for human lunar presence is real. The question is not whether robots can replace human presence entirely. They cannot, for science that requires genuine contextual intelligence. The question is whether we are being honest with ourselves about what human presence will cost, not just in dollars, but in health, in safety, in lives, and whether the benefits of that human presence, as currently planned, justify those costs. The answer to that question depends on what we're honest about, and honesty has not always been the defining characteristic of space agency communications to the public. The backup planet problem. And this brings us to the argument that drives much of the current enthusiasm for lunar settlement and, beyond it, for Mars colonization. The idea that humanity needs a backup planet, that we need to become a multiplanetary species as a matter of existential insurance against catastrophic events on Earth. Asteroid impacts, supervolcanic eruptions, climate change, pandemic, nuclear war, pick your civilizational threat. The argument, made prominently by people who can afford rockets, is that the survival of humanity requires us to establish a self-sustaining colony somewhere else. The moon, in this framing, is the first step, practice ground, proving ground, the place where we develop the technology and the knowledge and the institutional experience to eventually do Mars. It's compelling. It's resonant with human history, the explorers who crossed oceans, the settlers who crossed continents, the species that has never been content to stay in one place. But there are several things wrong with this argument that deserve to be said plainly. First, none of the challenges described in this video get easier on Mars. The radiation is similar, actually slightly worse in some respects, since Mars receives more cosmic rays than the Moon due to its distance from the Sun and the limited protection offered by its thin atmosphere. The dust on Mars is arguably even more problematic. Martian dust storms can blanket the entire planet for months, as we saw in 2018, when a global dust storm ended the Opportunity rover's mission. The psychological isolation is incomparably worse. Communication delays on Mars range from 3 to 24 minutes each way. A medical emergency cannot be answered by anyone within dozens of light minutes at minimum. You are not a 3-day emergency return away from help. You are a 7-month journey away. Second, the kind of colony that would actually constitute meaningful insurance for humanity. A self-sustaining population of at minimum tens of thousands of people, completely independent of Earth for energy, food, water, manufacturing, medicine, and culture, is not something any current space program is remotely close to achieving, or has a credible plan to achieve in any realistic time frame. The Artemis program aims to put a small number of astronauts on the lunar surface for short periods. This is valuable science. It is not a backup civilization. Third, the framing of space colonization as a solution to Earth's problems is, at minimum, a distraction. The most plausible existential threats to human civilization, climate change, pandemic, biodiversity collapse, political instability, are problems that can, in principle, be addressed here, on Earth, with resources and attention that would otherwise be directed elsewhere. Building a colony on the Moon does nothing to make Earth's atmosphere more stable, its oceans less acidic, its ecosystems more resilient. The backup planet argument can function as a permission structure for not fixing the problems we have, by implying that we can always leave. Terraforming the Moon is not a serious near-term proposal. It would require, at minimum, introducing a substantial atmosphere, something the Moon's weak gravity cannot retain over geological timescales. Any atmosphere we might give the Moon would slowly leak away into space over millions of years, because the escape velocity of the Moon is only 2.38 kilometers per second, far below what is needed to retain nitrogen and oxygen over geological time. We could not terraform the Moon in any permanent sense. We could at best create temporary, maintained artificial environments, which is exactly what a space station does, just slightly closer to the ground. What all of this means. And yet, we are going back. The Artemis program is real. The Chinese lunar exploration program is real. India's ISRO has demonstrated South Polar landing capability. The commercial space industry is building hardware for lunar missions with genuine urgency. We are going back to the Moon, and eventually we will go to Mars, and human beings will live in space for extended periods, probably within the lifetime of most people watching this video. The question is not whether we should go. The question is whether we should go with open eyes, with a full and honest accounting of what the Moon will cost us and what it will try to take from us, rather than with the comfortable mythology of easy conquest and infinite frontier. The Apollo astronauts went with inadequate knowledge of the dust. They were lucky that the consequences were limited to hay fever symptoms rather than chronic lung disease. Future missions will be longer. Exposure will be greater. The dust problem needs to be solved before people stay for months, not managed with the equivalent of Apollo's tape and prayers approach. The radiation problem needs a genuine engineering solution, not a hope that solar weather will be quiet. The thermal cycling problem needs materials tested over years, not days. The seismic risk near active fault zones needs to be taken seriously when choosing landing sites, not explained away as acceptable probability. The psychological dimension needs countermeasures as sophisticated as the life support systems themselves. The Moon is not going to cooperate with our plans. It never has. The 12 people who walked on it came home, and we celebrated, and we told ourselves we had conquered something. We had not conquered it. We had visited it briefly and survived, partly due to engineering, partly due to preparation, and partly due to luck we cannot rely on when we go back and decide to stay. The moon is, as always, waiting, quiet, patient, covered in glass powder that hasn't moved in 1,000,000 years, bathed in radiation from dead stars, shaking itself apart along fault lines that haven't been mapped and have not been told they need to stop, swinging through its relentless temperature cycle with the mechanical indifference of a world that existed for 4 billion years before the first single-celled organism appeared on Earth and will exist for billions more after we're gone. It looks peaceful from here. It always does. The moon, as always, will be waiting. We went there 6 times. Each time we stayed for less than 3 days. We were visitors passing through too quickly for any of these dangers to fully reveal themselves. 6 brief landings across 6 years, the entire program canceled before it had been running long enough to encounter the worst of what the lunar environment could throw at a human being. Going back is one thing, staying is something else entirely. The engineers who will design the habitats for the Artemis base camp know about the dust. They know about the radiation. They know about the thermal cycling and the seismic risk and the psychological challenges. They are working on solutions to all of them. Genuinely smart people putting enormous effort into problems that have no easy answers. They may solve them. Human ingenuity has solved problems that seemed equally impossible before they were solved. But we should watch this unfold with clear eyes and honest expectations, not with the breezy confidence of people who have forgotten that the 12 men who planted flags in the lunar dust came home because they were brave, well-prepared, and fortunate. And that fortune is not a variable we get to specify in a mission plan. The moon, as always, will be waiting, quiet, patient, and far more hostile than it looks. I hope you enjoyed the video. If you did, please leave a like. It genuinely helps this channel grow and lets me know you want more content like this. And if you're not subscribed yet, hit that subscribe button and the notification bell so you don't miss future videos. We cover science, space, and the kinds of facts that change how you see the world. I'll see you in the next one.